Hello, dear student. I'm your chemistry teacher, Miss Sunny.
Hey, welcome. Have you ever really stopped to think about what holds a drop of water together? Or, what decides if something's a solid, a liquid, or a gas? Well, the answers are hiding in this secret world of invisible forces that work between molecules. So let's dive right in and uncover these forces that pretty much shape everything around us. All right, to get started, let's talk about something we all think we know: water. I mean, it's everywhere, right? But from a chemistry standpoint, it is a complete and total oddball. For a molecule that's so tiny and lightweight, its boiling point is just ridiculously high. And believe me, that's not even its weirdest trick. You've seen this a million times, right? Ice cubes floating in your drink. But hold on, think about that for a second. For almost every other substance out there, the solid version is denser than the liquid, so it sinks. But water? Nope. Ice floats because it's actually less dense. So why is that? To crack this mystery, we've got to investigate the forces at play. And that, right there, brings us to our main event. The culprits behind all these strange properties are what we call intermolecular forces. The best way to think of them is like an invisible glue that makes molecules want to stick together. And this glue is what governs their physical properties, things like boiling points, melting points, and even density. So what are these things, really? Well, intermolecular forces, or IMFs for short, are these attractive forces that exist between separate molecules. They're the whole reason molecules in a liquid, for example, hang out together instead of just flying off in every direction like they do in a gas. Now, here's something that is absolutely crucial to get right. Do not mix these up with intramolecular forces. See the difference? Inter means between, intra means within. Intramolecular forces are the super strong covalent bonds that hold the atoms together within a single molecule. Intermolecular forces are the much, much weaker attractions between different molecules. So when you boil water, you're just breaking those weaker intermolecular forces to let the molecules escape as steam. You are not breaking the super strong HOH bonds inside the water molecules themselves. That would take way more energy. Okay, so it turns out there isn't just one type of this molecular glue. Not at all. There's a whole spectrum of stickiness, a whole lineup of different forces. So let's play detective and profile the main suspects, from the weakest all the way up to the strongest. So here's our lineup. We've got three main players, and they get stronger as we go down the list. First up, we have the universal but weakest one, and its full name is a bit of a mouthful: instantaneous dipole-induced dipole forces. Then, moving up in strength, we get permanent dipole-dipole forces. And finally, the undisputed superstar of the group, hydrogen bonding. All right, let's start with our first suspect. This is the weakest one of the bunch, but it's also the most fundamental. In fact, it's totally universal. It exists between all molecules, no exceptions. So here's how this works. Inside any atom or molecule, you've got electrons that are just constantly whizzing around. Now, just by pure chance, at any given microsecond, you might get more electrons on one side of the molecule than the other. This creates a temporary lopsided charge, a little fleeting positive end and a negative end. We call that an instantaneous dipole. Well, this temporary dipole can then influence the electrons in a neighboring molecule, creating what we call an induced dipole. And it's that brief, fleeting attraction between them that creates this weak force. And we can see this effect in action right here in this table. If you take these simple molecules called alkanes, you can see that as the molecules get bigger, from methane to butane, they have more electrons. And more electrons means a greater chance for these temporary dipoles to pop up, which makes the forces between them stronger. So what happens to the boiling point? Look at that, it just steadily climbs. It takes more and more energy to pull these bigger, stickier molecules apart. Okay, next up in our lineup is a stronger and a little more selective kind of force. This one doesn't apply to everybody. It only works for a special class of molecules we call polar molecules. This is the permanent dipole-dipole force. It happens with molecules like hydrogen chloride or HCl that have a permanent separation of charge. One end of the molecule is always a little bit positive, and the other end is always a little bit negative. They literally act like tiny little magnets, with the positive end of one molecule attracting the negative end of its neighbor. And that brings us to our final suspect, the heavyweight champion of these intermolecular attractions. This one is really just a special, souped-up version of the dipole-dipole force, and it is incredibly important for, well, pretty much everything. And this is hydrogen bonding. It has a very specific rule. It only happens when a hydrogen atom is bonded to one of three very particular elements: nitrogen, oxygen, or fluorine. These atoms are what we call highly electronegative, which is just a fancy way of saying they are really good at hogging electrons. This makes the bond superpolar, leaving the tiny hydrogen atom with a strong partial positive charge. This exposed positive hydrogen is then powerfully attracted to the electrons on a neighboring nitrogen, oxygen, or fluorine atom. It's a really, really strong attraction, as you can see in this diagram between water molecules. Okay, we now have all the pieces of the puzzle. We've profiled our forces from weakest to strongest, and now we can finally go back and solve the mystery we started with, the very, very weird behavior of water. So why does ice float? The answer is hydrogen bonds. See, in liquid water, the molecules are all jumbled up and sliding past each other. But as water freezes, those powerful hydrogen bonds take over, and they lock the molecules into this really organized three-dimensional crystal structure. And if you look at the diagram, you can see how this structure is surprisingly open. There's a lot of empty space in there, which forces the molecules to be farther apart than they are in the liquid. More volume for the same amount of stuff means lower density, and that right there is why ice floats. Case closed. And this brings up a really key point of perspective. As strong as hydrogen bonds are, and they are the strongest of the intermolecular forces, we have to remember what our source material points out. The forces between molecules are much weaker than covalent bonds. Keeping this in mind makes what we're about to see even more amazing. This graph right here is the smoking gun. Just look at this. If you check out the compounds from group 16, you see a really clear trend. As the molecules get heavier, the boiling point goes up. So if you followed that trend, you'd expect water, H2O, to have the lowest boiling point of the whole group, somewhere way down here in the negative temperatures. But look at it. It's a massive outlier, soaring way up at 100 degrees Celsius. And you see the exact same thing with HF and NH3 in their groups. And the reason for this dramatic break in the trend? You guessed it, hydrogen bonding. It just takes a ton of extra energy to break those powerful attractions. Let's just break it down with this simple comparison. Methane, which only has those weak, fleeting forces, it boils at minus 162 degrees. Then you have HCl with its stronger, permanent dipole forces, and it boils at minus 85. And then there's water with its superstar hydrogen bonds boiling at a whopping 100 degrees Celsius. The relationship couldn't be clearer. The stronger the force between the molecules, the more energy you need to pump in to pull them apart. Okay, so let's zoom out one last time and put all of this into the big picture. We've said that these intermolecular forces are weaker than actual chemical bonds. But just how much weaker are we talking about? This table tells the whole story, and it is jaw-dropping. To overcome the intermolecular forces in methane and boil it, you only need to get down to about minus 162 degrees. But to break the ionic bonds in table salt, you need to get to over 1400 degrees. For the metallic bonds in iron, almost 3000 degrees. And for the covalent bonds in a diamond, a mind-boggling 4000 degrees Celsius. The difference in strength is just absolutely immense. And yet, and this is the amazing part, even though we call them weak forces, they are powerful enough to decide whether something is a solid, a liquid, or a gas. They are the entire reason water is a liquid on Earth, which, is the very foundation for life as we know it. I mean, think about it. From the exact shape of proteins in our body to the way the two strands of our DNA are held together, these forces are everywhere, governing the very architecture of life itself. So it makes you wonder, if these so-called weak forces are responsible for all of this, what other incredible secrets are still hiding in that invisible glue that holds our entire world together?